Thank you, Jan, and welcome. And my God, thank you for this. It's a highlight of my year, the opportunity to talk to you. I don't know what you can see right now, but there are 2,000 of the smartest people on the planet watching you from Cambridge. And boy, what an opportunity to pick your brain.
He's in stereo. Look at that one.
Well, I can see them from the back.
Okay. Yeah, actually, if you want Jan to see your face, he's behind you too. So Jan, what an amazing coincidence. Llama 3 dropped just while we were meeting today. What are the odds?
That's
Unbelievable. So, absolutely staggering. So what came out today was 8B, Llama 3, 8 billion, and 70B. So far, what we're hearing in the rumor mill is that the 8B performs as well as the old Llama 2 70B did. So we're looking at an order of magnitude change. Does it sound about right to you? Also, I noticed it was trained on 15 trillion parameters. Where did you come up, or 15 trillion tokens? Where did you come up with 15 trillion tokens? What can you tell us?
Okay, so the first thing I have to say is that I deserve no credit whatsoever for Llama 3. Maybe a little bit of credit for making sure our models are open source, but technical technical contributions are from a very large collection of people and have very, very small part of it. So 15 trillion tokens, yeah. I mean, you need to get all the data you can get, all the high quality public data, and then fine tune and license data and everything. So that's how you get to 15 trillion. But that's kind of a bit, it's kind of saturating. Like there is only so much text you can get, and that's about it.
Well, I got to say, I owe a big fraction of my life journey to you. You didn't know it, but when you were doing optical character recognition way back in the day, I was reading your CNN papers. He invented convolutional neural nets, which really made those things work. That became my very first dollar of revenue I ever made in a startup, was doing neural networks based on your work. Changed the course of my life. Wow. Now, you're doing it again, especially for you young folks in the front here. By being the champion of open source, I think you're fundamentally giving them an opportunity to build companies that otherwise wouldn't be able to be built. So first of all, huge debt of gratitude for you for championing that. So the next thing that happens could be one of those events we look back on in history and say that was a turning point for humanity. The 750B monster neural net will come out soon. Will also be open source, I assume?
4 or 5B, from what I gather, about 400 million.
About 400 million?
Billion.
Okay. Billion, yeah. Okay.
Yeah. Dense, not sparse, which is interesting. So yeah, it's still training. Despite all the computers we have our hands on, it still takes a lot of time. Takes a lot of time to fine tune.
Yeah.
But it's going to come out. A bunch of those, variations of those models are going to come out over the next few months.
Yeah, I was going to ask that question next. So they didn't come out concurrently, which is interesting, which means it must still be in the training process. It's such a massive endeavor. And I saw in the news that Facebook had bought another 500,000 NVIDIA chips, bringing the total to about 1 million. By my math, unless you got a discount, you might have gotten a volume discount, but that's $30 billion worth of chips, which would make the training of this model bigger than the Apollo moon mission in terms of research and development. Am I getting that about right?
It's staggering, isn't it? Yeah, I mean, a lot of, not just training, but also deployment is limited by computational abilities. I think one of the issues that we're facing, of course, is the supply of GPUs. Mm-hmm. That's one of them, and the cost of them at the moment. But another one is actually scaling up the learning algorithm so that they can be parallelized on lots and lots of GPUs. And progress on this has been kind of slow, like in the community. So I think we're kind of waiting for breakthroughs there. But we're also waiting for other breakthroughs that are, in terms of architectures, like new principles, new like brand new blueprints with which to build AI systems that would enable them to do things they can't do today.
Mm-hmm. And so, since you brought it up, the philosophy of taking an investment that size and then open sourcing it, there's no historical precedent for this. And the equivalent would be if you built a gigafactory that builds Teslas, and somehow you gave it to society. But the thing is, once you open source it, it can be infinitely copied. So it's not even a good analogy to talk about a gigafactory being open sourced. So there's no precedent for this in business history. What's the logic behind making it open source? What do you want to see happen from this?
Well, so what's happened, I mean, certainly the whole idea of open sourcing infrastructure, software, is very prevalent today. And it's been in the DNA of Meta, Facebook before that, since the beginning. There's a lot of open source packages that are basically infrastructure software that Meta has been open sourcing over the years, including in AI, right? So everybody is using PyTorch. Well, everybody except a few people at Google, but pretty much everybody is using PyTorch. And that's open source. It was built originally at Meta. Meta actually transferred the ownership of PyTorch to the Linux Foundation. So it could be much more of a kind of community effort. So that's really in the DNA of the company. And the reason is, infrastructure is better, becomes better faster when it's open source, when more people contribute to it, when there is sort of more eyeballs looking at it. It's more secure as well.
Yeah.
So what is true for, internet infrastructure software is also true for AI. And then there is the additional thing for AI, which is that foundation models are so expensive to train. It would be a complete waste of resources to, have 50 different entities training their own foundation model. I mean, it's much better if there is only a few, but they make them open, and that basically creates the substrate for a whole ecosystem to take off. And it's very much the same thing that happened to the internet in the 90s. If you remember, in the mid-90s, when the internet started to get popular, the software infrastructure was dominated by proprietary platforms from either Microsoft or Sun Microsystems. And they both lost. They kind of disappeared from that market. Now it's all Linux, Apache, MySQL, PHP, whatever. All the open source stuff, even the core of web browsers is open source. Even the software stack of cell phone towers is open source nowadays. So infrastructure needs to be open source. It just makes it progress faster, be more secure, and everything.
Well, I'm so glad to hear you say that, because there are definitely diverging philosophies on that if you think about where OpenAI is going and where you're going. But the version of the world that you're describing is one where all of these startups and all of these teams can thrive and be competitive and create and innovate. And the alternate version is the one where strong AI is invented in a box and is controlled by a very small group of people, and all the benefit confers to a very small group. So I don't have skin in the game on this, but I certainly love your version of the future a lot more than alternate versions. So very, very glad to hear you say it. So I want to spend a lot of our time, or a limited time that we have, talking about the implications of this and where you see it going. I also want to ask you about V-JEPA. So you've been very clear in saying that LLMs will take us down a path of incredible things we can build, but it's not going to get you to a truly intelligent system. You need experience in the world. And V-JEPA, I think, is your solution to that. Is that going to carry us to that goal? Tell us about V-JEPA, first of all.
Okay. Well, first of all, I have to, tell you where I believe AI research is going. And I wrote a fairly long kind of vision paper about this about 2 years ago that I put online that you can look for. It's on Open Review. It's called A Path Towards Autonomous Machine Intelligence. I replaced the autonomous by advanced now because people are scared by the word autonomous. So we have this thing, autonomous or advanced machine intelligence, that's spelled AMI, and in French you pronounce this ami, that means friend, in French, which I think is a good analogy. Anyway, current LLMs are very limited in their abilities, and Stephen Wolfram just before actually pointed to that limitations as well. One of them is they don't understand the world. They don't understand the physical world. The second one is they don't have persistent memory. The third one is they can't really reason in the sense that we usually understand reasoning. They can regurgitate previous reasoning that they've been trained on, and adapt them to the situation, but really not reason in the sense that we understand it for humans and many animals. And the last thing, which is also important, they can't really plan either. they can again regurgitate plans that they've been trained on, but really plan in new situations they can't. And there is a lot of studies, by various people that show the limitations of LLMs for planning, reasoning, and understanding the world, etc. So we need to basically design new architectures, which would be very different from the ones we currently have, that will make AI systems understand the world, have persistent memory, reason, plan, and also be controllable in a way that you can give them objectives, and the only thing they can do is fulfill those objectives and not do anything else, subject to some guardrails. So that's what will make them safe and controllable as well. So the missing part is, how do we get AI system to understand the world by watching it, a little bit like baby animals and humans? It takes a very long time for baby humans to really understand how the world works. Like the whole idea of the fact that an object that is not supported falls because of gravity. It takes 9 months for human babies to learn this. It's not something you're born with. It's something you have to observe the world and sort of understand the dynamics of it, right? How do we reproduce this ability with machines? So for almost 10 years now, my colleagues and I have been trying to train a system to basically do video prediction, with the idea that if you get a system to predict what's going to happen in the video, it's got to develop some understanding of the nature of the physical world. And it's been basically a complete failure. And we tried many, many things for many years. But then a few years ago, what we realized is that the architectures that we can use to train deep learning systems to learn representations of images are not generative. They are not things for which you take an image, you corrupt it, and then you train a system to reconstruct the uncorrupted image, right? Which is the way we train LLMs, right? That's how we train LLMs, where we take a piece of text, we remove some of the words, and train some gigantic neural net to predict the words that are missing. If you do this with images or video, it doesn't work. Or, I mean, it kind of works, but you get representations of images and videos that are not very good. And the reason is, it's very difficult to actually reconstruct all the details of an image or a video that is hidden from you. And so what we figured out a few years ago is that the way to approach that problem is through what we call a joint embedding architecture, or a joint embedding predictive architecture, which is what JEPA means. It's an acronym. And the idea of joint embedding architecture goes back to the early 90s. Some people I worked on, we used to call them Siamese nets. But the idea is basically, if you have, let's say, a piece of video, and you mask some parts of it, let's say the second half of the video, and then you train a big neural net to try to predict what's going to happen next in the video, that would be a generative model. Instead of that, we run both videos through encoders, and then we train a predictor in the representation space to predict the representation of the video, not all the pixels of the video. And you train the whole thing simultaneously. We didn't know how to do this 4 years ago, and we kind of figured out a number of ways to do this. We now have half a dozen algorithms for this. So V-JEPA is a particular instance of this kind of thing, and the results are very promising. I think ultimately we're going to be able to build or train systems that basically have mental world models, have some notion of intuitive physics, have some possibility of predicting what's going to happen in the world as a result of taking an action, for example. And if you have a model of the world of this type, then you can do planning. You can plan a sequence of actions to arrive at a particular objective. And that's really what intelligence is about. That's what we can do.
So I think that's a really critical question, actually. Because when you use diffusion algorithms to create pictures, they'll make 6 fingers or 4 fingers all the time. They never make 5 fingers. But these LLMs have a shocking amount of common sense, but they also are missing a shocking amount of common sense. Once you roll in the JEPA data, the V-JEPA data, you give it a lot more of an opportunity to think much more like we do, because all the real world experiences of moving around and feeling things are folded into the training data. So do you think the result of that will then be one massive foundation model, or are we still going to use the mixture of experts approach and glue them together in kind of synthetic ways?
I think ultimately it's probably going to be one big model. Of course, it'd be modular in the sense that there's going to be multiple modules that interact but are not necessarily completely connected with each other. There's a big big debate now, in AI, whether if you want a multimodal system that deals with text as well as images and video, should you do early fusion? So should you basically tokenize images or videos and then turn them into kind of little vectors that you concatenate with, with the text tokens? Or should you do late fusion, which means, run your images or video through some sort of encoder that is more or less specialized for it, and then have some merging at the top. I'm more in favor of the second approach, but a lot of the current approaches actually are more early fusion because it's easier, it's simpler.
Well, I'm gonna do the dangerous thing of asking you to predict the future, but if you can't, then nobody can. So it has to be you. So once you roll in the V-JEPA data and you train these massive models, and suppose you go up another 10x, buy another $30 billion or so of chips. The combination of the V-JEPA data plus this massive scale, will that be enough to then solve fundamental problems like physics problems and biological experimentation problems? Or are we still missing something in the pathway that needs to be thought of and added after that?
Well, I mean, it's clear that we're missing a number of things. The problem is that we don't exactly know what, and we can see the first obstacle really, but like where is that going afterward is not clear. But the hope is that we're going to get systems that can have some level of common sense. At first they're not going to be as smart as a top mathematician or physicist, but they're going to be as smart as your cat. That would be a good, pretty good advance already.
Okay.
If we had systems that were, as could understand the world like cats. If you had systems that could be trained very easily in 10 minutes, like any 10-year-old, to clear up the dinner table and fill up the dishwasher, we would have domestic robots. If we had systems that could learn to drive a car in 20 hours of practice, like any 17-year-old, that would be a big advantage.
Hey, Jan, I'm interrupting here for a sec.
It's going to take a while.
Jan, so, we spoke at the Time Party at Davos on this subject, and we enjoyed having you at Imagination Action in the Dome. This is the second of 3 of our events. I don't know if you realize this, but if you speak at all 3, the next one's June 6th, you get a chia pet. This is a foot of a chia pet. So, and I think a chia pet would go great there. Did you enjoy speaking under the dome, not the MIT dome, but the MIT event in Davos?
Yeah, that was fun. Yeah.
All right. Can I lock you in for next year?
There was a spectrum of of people from the sort of techno-positive optimists, and I was not at the end of that spectrum, and the other side, doomers who think.
Oh, there's some doomers. It's Davos.
Yeah. All right. Well, we have someone from OpenAI, and given that you work at Meta, you may not want to be seen in the same Zoom. So, ladies and gentlemen, Jan LeCode.
Thank you, Jan.
All right. Thank you. Well done.